This is MEG 224, Engineering Mechanics 2, Dynamics. We're going to look at lecture 5. That is kinetics of particles. And that one is about the principles of impulse and momentum. This can be found in chapter 15 of Engineering Mechanics, Dynamics by R.C. Hibler. Lecture objective for part A. This lecture 15 has been divided into 3 parts for easy assimilation and then easy follow-up. So for lecture A, or for part A, the lecture objectives are: we're going to develop the principle of linear impulse and momentum for a particle and apply it to solve problems that involve force, velocity, and time. Then we're going to study the conservation of linear momentum for particles. Principle of linear impulse and momentum. In this section, the equation of motion with respect to time will be integrated, and thereby we're going to obtain the principle of impulse and momentum. The resulting equation will be useful for solving problems involving force, velocity, and time. Using kinematics, the equation of motion, F is equal to ma, of a particle of mass m can be written as this. That is, summation F is equal to ma, which is equal to m dv dt, where a is the acceleration and m is the mass and v is the velocity of that particle. We can rearrange the terms and integrate between the limits at time t is equal to t1, then v will be equal to v1. At time t equals t2, v will be equal to v2. So rearranging, you can have that summation of integral f dt is equal to m integral dv, integrating from v1 to v2. So this one we now have integral f dt is equal to mv2 minus mv1. So this mv2 is the final momentum and mv1 is the initial momentum. This is the change in momentum, and this f dt is impulse. So this equation is referred to as the principle of linear impulse and momentum. On the left, we have impulse, while on the right, we have change in momentum. It is a simple time integration of the equation of motion. It provides a direct means of obtaining the particle's final velocity v2 after a specified time of period when the particle's initial velocity is known and the forces acting on the particle are either constant or can be expressed as a function of time. So once you know the force that is acting on a particle for a specified time and you know the mass, you can find either the impulse for that time or within that period, or find the change in momentum. So we now go on to linear momentum. Each of the two vectors of the form L is equal to mv here is referred to as the particle's linear momentum. Since m is positive, because you can't have a negative mass, and there is a positive scalar, then the linear momentum vector has the same direction as velocity, and its magnitude mv has the same unit as the unit of mass and velocity. So here we now have that this will now be kg meters per second, where kg is for the mass and then m meters per second is for the velocity. The linear integral, linear impulse, the linear integral I integral f dt is referred to as the linear impulse, as a linear impulse. This term is a vector quantity which measures the effect of a force during the time the force acts. Since time is a positive scalar, the impulse acts in the same direction as the force, and its magnitude has units of force time. So the magnitude of impulse I equals integral T1, T2, F dt. The unit is Newton seconds, because force is measured in Newton, while time is measured in seconds. So when we have constant force that is acting on the particle, if the force is expressed as if in particular, if the force is constant in both magnitude and direction, the resulting impulse becomes I is equal to Fc dt. That is, I equals integral Fc dt, where Fc is a constant force. So graphically, the magnitude of the impulse can be expressed by the shaded area under the curve of force versus time. And that is shown here. This is force. This is the force axis, and this is time axis. And then this shaded portion here is the impulse. The impulse. And here, the force is not constant. You can see that the force is not constant. So a constant force creates a shaded rectangular area, as shown here. Shaded rectangular area, as shown here. So you can see that the force is constant from T1 to T2. So we now move on to principle of linear impulse and momentum. We know that initially our equation is summation f integral f dt, which starts from T1 to T2, is equal to mv2 minus mv1. So This second term, we now carry it all over to this left-hand side. So we now have mv1 plus integral f dt is equal to mv2. So because by the time you carry minus mv1, it becomes plus on the left-hand side. So when we write in that form, in this form, that mv1 plus integral f dt is equal to mv2, then we can state the principle of linear momentum of a particle as the initial momentum of the particle at a time plus the sum of all the impulses applied to that particle from T1 to T2 is equivalent to the final momentum of the particle at that time. So it can be illustrated graphically as shown here, that the initial momentum plus all the impulses applied to the system or to the particle will give us the final momentum of that particle. Similarly, to the free body diagram, the impulse diagram is an outlined shape of the particle showing all the impulses that act on the particle when it is located at some intermediate points along its path. If each of the vectors in this equation here is separated, we know this is a linear system, a linear impulse, linear momentum. And it's happening in the inertial frame, inertial Cartesian frame. Then it can be resolved into three different axes: x-axis, y-axis, and then the z-axis. So for the y-axis, we'll have the for the x-axis, we have the x component of v1, which is mvx1. Then fx is equal to mvx2. Then for the y component, we have mvy1 integral fy dt equals mvy2. Then in the z direction, mvz1 plus integral fz dt will give us mvz2. The principle of linear impulse and linear momentum for a system of particles. We had already developed the principle for linear impulse and linear momentum for a particle. So that one will now be applied to system of particles. The principle of linear impulse and linear momentum for a system of particles moving relative to an initial frame is obtained from the equation of motion applied to all the particles in the system. This is the system, and we have different particles. So, and we have applied the principle of equation of motion to a particle, to one specific particle I. Therefore, the equation of motion is summation Fi is equal to summation mi dvi dt. The term on the left represents only the sum of the external forces acting on the particles. Recall that the internal forces Fi acting between particles do not appear in this summation because By Newton's third law of motion, they occur in equal but opposite linear pairs, and therefore they cancel out. So when we multiply both sides by dt, so we have summation fi dt, which is equal to summation fi dvi. And then we now integrate the two sides with respect to time and v at time t is equal to t1, v is equal to v1. When t is equal to t2, v is equal to v2. Then we have this equation, which states that the initial linear momenta of the system plus the impulses of all the external forces acting on the system from T1 to T2 is equal to the system's final linear momenta. Since the location of the center mass of the system is determined from equation this, that is MRG is equal to MIRI, where M is equal to summation MI, that is the total mass or the summing up of all the mass of all the particles. So if we now take the time derivatives of the two sides, RG dt, RI dt, what will be left will be MVG is equal to summation MI VI. Because when you differentiate displacement, what you have or what you come to is velocity. And this says that the total linear momentum of the system of particles is equivalent to the linear momentum of the fictitious aggregate particles of mass mi moving with the velocity of the mass center. So here, the initial, okay, so this one now yields that mvg plus integral fi dt is equal to mvg2. So initial momentum plus, or the initial momentum of the, considering the velocity of the center of the particles or the system of particles, plus the total forces or impulses applied to the system of particles will give you the final momentum of the center of gravity of the, or the mass center of the system of particles. So conservation of linear momentum for a system of particles. When the sum of the external impulses acting on a system of particles is zero, then we have this equation that is all the impulses, that is all the external forces, those forces do not produce any impulse. So this equation is referred to as the conservation of linear momentum, which states that the linear momentum of for a system of particles remain constant during the time T1 to T2. So we know that MVG is equal to summation MVI. So we can also write that VG1 is equal to VG2, that is the velocity of the mass center of the system. The initial velocity of the mass center of the system is equal to the initial the final velocity of the mass center of the system, which indicates that the velocity Vg of the mass center for the system of the particle do not change if no external impulse are applied to the system. The conservation of linear momentum is often applied when particles collide or interact. For application, a careful study of the free body diagram for the entire system of particles should be made in order to identify the forces which create either the external or internal impulses and thereby determine in what direction linear momentum is conserved. Now, as stated earlier, the internal impulses for the system will always cancel out because they occur in equal but opposite collinear pairs. If the time period over which the motion is studied is very short, some of the external impulses may also be neglected or considered to be equal to zero. The forces causing these negligible impulses are called non-impulsive forces. By comparison, forces which are very large and act for a short period of time produce a significant change in momentum and are called impulsive forces. They, of course, cannot be neglected in the impulse momentum analysis. Impulse forces or impulsive forces normally occur due to an explosion or the striking of one body against another, whereas non-impulsive forces may include the weight of a body, the force impacted by a slightly deformed spring, having a relatively small stiffness, or for that matter, any force that is very small compared to other large impulsive forces. When making this distinction between impulsive and non-impulsive forces, it is important to realize that this applies during the time T1 to T2, that is, when you are looking for whether the force is impulsive or non-impulsive, you want to have the distinction between them, then there must be time limit, T1 to T2. To illustrate, consider the effect of striking a tennis ball with a racket. During the very short time of interaction, the force of the racket on the ball is impulsive, since it causes a change in the ball's momentum drastically. By comparison, the ball's weight will have a negligible effect on the change in the momentum, and therefore it is not impulsive. Consequently, it can be neglected from an impulsive momentum analysis during this time. If an impulsive momentum analysis is considered during the much longer time of flight after the racket ball interaction, then the impulse of the ball's weight is important, since it, along with air resistance, causes the change in the momentum of the ball. Thank you. This is end of party. Do not forget to like this video, to subscribe, and to share. Then you press the notification bell for new videos. Thank you. And if you are my student, if you are my university undergraduate student or one of my university undergraduate students, please do not forget to subscribe with your matric number _ your name. Thank you.